Hi everyone. Today we're going to be talking about topic 1.5, atomic structure and electron configuration. So a lot of these earlier slides that I'm going to be covering in this video are more so background just about how electron orbitals work and orbital diagrams work in the background behind all of that, not necessarily things that you need to write down and copy verbatim. These slides are posted so you can look on there if there's anything else you want to know. But the most prevalent model that we typically see in the media is the Bohr model, which was shown right over here on the right, where you typically have our nucleus right at the center and electrons orbiting around that nucleus. It's a very simple model, and the key ideas are that electrons only exist in certain discrete energy levels, which are described by quantum numbers, and I'll get into what those mean later. And energy is required to transition an electron from one level to another level. A big limitation is that it really only works for hydrogen. Any other element, it kind of falls apart. Classical physics says that the electron should fall into the nucleus, although of course it doesn't. We know that the electrons orbit the nucleus, and then circular motion is not very wave-like in nature. And so what I mean by that is that later models proposed by Werner Heisenberg showed that electrons don't necessarily orbit the nucleus in a circular fashion like the Bohr model says, but instead the electrons behave both as a wave as well as a particle. The Bohr model likes to favor particles, but this Heisenberg model showed that electrons are more like both a wave and a particle. What he also showed is that electrons, we don't know their precise momentum as well as their precise position at any moment. And that isn't due to any limitations due to our instrumentation or of our knowledge. That is something that is just not possible to be known. You cannot know both the position as well as the momentum of an electron or any particle in general. So the result of that is basically if you want to figure out where electrons are orbiting around the nucleus of an atom, you can't precisely know where they are. And so rather than saying that we know exactly where an electron is inside of an orbital, we have these density functions known as wave functions. One of them is shown here on the right, which is the wave function for the 1s shell of hydrogen. What it basically is an equation similar to an equation that you would see in math that predicts the probability of finding an electron in a particular region around an atom. And so for this one, this is the 1s orbital. It's saying that you have a very high probability of finding an electron in this cloud here, but you may also find an electron further out around here in this kind of lower probability region. All right, and so if we start thinking about the orbitals around a nucleus, we have first the s orbitals. These are spherical in nature. As you can see, this particle diagram here shows pretty much a circle around that nucleus, and they increase in size by their principal quantum number, which is this 1, 2, and 3 right here. So increase in size with principal quantum number. Now, the important thing here to remember is that it holds 2 electrons. And so s orbitals can only hold 2 electrons. Next, we have our p orbitals. And again, here's our density function right here that shows that there's a high probability of electrons here as well as here. And if you notice, in between these two, we have this area where there are no electrons that are likely to be found. And this we call a node. And so for the p orbitals, we have 3 p orbitals, known as pz squared. Oh, sorry, just pz. Px, and py. And essentially, the direction of the orbital is whichever axis it's on a 3-coordinate graph. These, again, hold 2 electrons per p orbital. And once again, no electrons are found in the node. And so, because we have 3 different p orbitals and each hold 2 electrons, for the p orbitals, they hold 6 electrons total. Next, we have our d orbitals. As you can see here, there are 5 orbitals. And these kind of have a clover shape, and so they're called dyz, dxz, dxy, dx squared minus y squared, and then dz squared. So dyz, dxz, and dxy, you can see that all of these areas that have electrons are in between 2 orbitals two axes. And so for dyz, the electrons are between the z and the y-axis. For dxz, the electrons are between the z and the x-axis. And for dxy, the electrons are in between the x and y-axis. For dx squared minus y squared, all of the electrons are directly on the axes. And then we have dz squared, which is the weird one out of all of them, but there's 2 lobes on the z-axis and then this donut right here in the middle. And again, I want to point out in red pen, with all of these, there is a node directly in the middle where you don't expect to see any electrons. Similar to the s and the p orbitals, each orbital holds 2 electrons. And so 2 electrons times 5, the d orbitals hold 10 electrons total. Now finally, the f orbitals are the most complicated of all of them. You're not really expected to know what the shape of these orbitals are just because they're very complicated. But the only thing that I would suggest that you know is, again, right, each orbital holds 2 electrons. We have 7 orbitals total. So 2 electrons times 7 orbitals. The f block, or the f orbitals, hold a total of 14 electrons. Now, another key thing to remember is energy levels, right? You might see a diagram like this that's describing the energy of particular orbitals. The reason why this is important is because it tells us how our electrons are going to fill different orbitals of an atom. And so you always start from the lowest energy and then move up, right? So our 1s orbital is our lowest energy. Then we move on to the 2s orbital, 2p, 3s orbital, 3p, I'm sure you can see a trend here, 4s orbital, and then when we get to the d's, things get a little funky, and the 3d orbital is slightly higher energy than the 4s orbital, and then you go back to the 4p orbital right there. And so you kind of go 1, 2, 3, 4, back down to 3, and then back up to 4. Another important thing here that is stated right here is that orbitals in any subshell are degenerate, or they have the same energy. And that's basically saying that the pz orbital is equal to the py orbital is equal to the px orbital. There's no difference in the energy of those. What is different is the level or the number that's in front. And so that, again, that number in front is the principal quantum number. And that determines the energy levels, not the individual axis that the orbital is on. And now, if we relate all of this back to electron configuration, right? Our electron configuration tells us how electrons are distributed in a particular atom. And the most stable organization is called that ground state energy. And so each component of an electron configuration consists of a few parts. The first, this number denoting the energy level, is the principal quantum number in the front, which tells you the energy of the orbital. Then we have a letter denoting the type of orbital. In that case, it's S, P, D, or F. And then we have a superscript, which shows the number of electrons in those orbitals. And so this in particular is saying that it's at an energy level of 4 in a p orbital, and there are 5 electrons total in all the p orbitals of this atom. So a few slides ago, I was also showing you an orbital diagram that looked a little bit something like this, and you might often see this on the AP exam or just used to describe electron configuration other than the way that we've talked about it before, kind of showing the 1s2, 2s2, 2p6, etc., etc. And so in this case, boxes represent orbitals, and arrows represent electrons. And then the direction of the arrows tells you the spin of that electron. And so if you're trying to fill out a diagram like this, for example, we're going to look at fluorine, which is equal to, which its electron configuration is 1s2, 2s2, 2p5. What you would do is follow a few important rules, which I'm going to write here in blue. The first is the Aufbau principle. Which says that you fill electrons from low energy to high. Right, and so you're not going to start filling electrons up in the 2s or 2p or 3s orbital. You're going to start at the lowest energy, which is the 1s orbital. The other one is Hund's rule, which says that you fill as many electrons unpaired as possible. Right, and so you start filling these orbitals with only one electron before you start throwing another electron in that same orbital. Then the final one is the Pauli-Exclusion principle, which says that electrons in the same orbital have different spins. Right, and so in one orbital, you cannot just have, you cannot have two electrons that have the same spin. And so if I'm going to fill the orbital diagram of fluorine, what I'm going to do is first, remember Aufbau principle, you go from lowest energy to highest. So I'm going to do a half arrow up, and then because there's no other orbitals in the 1s shell, what I'm going to do is put my second electron right next to it. And remember, that electron should be pointing down because you should never have two electrons of the same spin in one orbital. Now 1s is filled, it only occupies 2 electrons, we move up to 2s. And again, we put one up and one down. There are no other orbitals in the 2s kind of energy level, and so we can move up to 2p. And in 2p, we have 5 electrons. And so we're going to first put one here, next put one here, because Hund's rule says that you're going to fill as many electrons unpaired as possible. And then we're going to put our third one right there. We still have 2 electrons left, and we still have 3 orbitals to fill. And so again, we will put another electron in the first 2p, this time pointing down because they should always have opposite spins. And our last electron is going to go right there in that second 2p orbital. And then our last 2p orbital is going to be unfilled unless you get another electron in there. In that case, we would have a different electron configuration. And if you're ever confused on things and want something to reference, the periodic table will tell you everything. And so different blocks in the periodic table correspond to different types of orbitals. Right, our s orbitals are right over here with our alkali metals and our alkali earth metals. Our p orbitals are all the way over here to the right. Things like where oxygen, fluorine, your halides, all of those are your p block elements. Then you have your d block, or your transition metals, things where you typically find iron, copper, nickel, all of those right there. Those will have d block electrons. And then finally, which we won't really talk about too much, are our f block elements. Those things all the way at the bottom of the periodic table that you typically never think about and are always kind of on their own, right? Those kind of slot right here next to the s orbitals when you get all the way down to that part of the periodic table. But if you're ever confused on order, just always look at the periodic table and remember that. Okay, so I want to take a little bit of time just to show some examples here. And so this question is asking, draw the orbital diagrams for the electron configuration of oxygen, atomic number 8. And then it asks a follow-up of how many unpaired electrons does oxygen have. And so I'm going to let y'all, pause the video, try and work this out on your own, and then I'm going to solve it in a second. Okay, so for this one, we got to remember our electron configuration for oxygen. If we look at the periodic table, we can see that it should be 1s2, 2s2, 2p4. And so if we're calling this our 1s, calling this our 2s, and then calling all of these our 2p, we know that, again, we start from our lowest energy level. So 1s, that should get 2 electrons. Then 2s, that should also get 2 electrons right there. And then 2p, we have 4. And so we should fill 1, 2, 3 all spin up and all on their own because we fill unpaired first, then throw our down electron into that first p orbital. So that would be our electron configuration. And then we would see that there should be 2 unpaired electrons in oxygen. Now here's another practice problem that you might want to consider. Which of the following is the ground state electron configuration of the F- ion? Now, if we think of fluorine typically, right, if we look at its position on the periodic table, we should have 1s2, 2s2, 2p5, right? That's typically what we think of the electron configuration of fluorine. But in this case, we have F-, right, a fluoride ion. And so we have 1 extra electron. That electron obviously isn't just floating around in random space. It should go into an orbital. And so far, typical electron configuration of fluorine is 1s2, 2s2, 2p5. Well, if we look at our orbital diagrams here, for fluorine, 1s should be filled. 2s should also be filled. Now 2p, we would typically put 1 here, 1 here, 1 here, then down and down. That final extra electron in our F- ion would go right there. And you can see that we've actually filled up our 2p orbital as well. And so the electron configuration of the F- ion should be 1s2, 2s2, 2p6, because we have that extra electron. And so C would be our answer in this case. Now, if you want a little bit more background on quantum numbers and what all of these things mean, here's kind of a table explaining that a little bit. Again, the assignment of quantum numbers and electron subshells will not be assessed on the AP exam, and so you don't need all of this in-depth information, but it might help you just appreciate what's going on and understand a little bit better. Anyway, that's it. Thanks, guys.